Hey everyone, this is our lesson for Monday, December 1st, 2025, and it is on radicals and rational exponents. So we recently worked with the quadratic formula, which involved a square root symbol. So here we go. We're going to just kind of build off of what we already know. So if you ever hear the phrase principal square root, unless a negative sign is written outside of the square root symbol, you always give the positive square root value. For instance, if someone was to say, hey, what's the square root of 16? We might say both 4 and negative 4 are the square roots of 16, since 4 times 4 is 16 and negative 4 times negative 4 is 16. However, this symbol that we're looking at, the principal square root symbol, always refers to the positive value. So in this example right here, when we see the symbol square root of 25, we simply give the value 5. Unless there's a negative sign outside of it, like we saw with the quadratic formula, then you would give a negative 5 value. And just please be careful with a negative sign inside of a square root. We discussed this in class, but there's no real number times itself that makes 25. So the answer, when you have a negative inside of a square root, is not a real number. So now we're going to talk about simplifying square roots. And our goal is to pull out any perfect square factors. So we've seen these numbers in class before: 4, 9, 16, 25, 36, 49, 64, 81, etc., etc., right? So 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc. And our goal, again, is to pull out any perfect square factor from a square root. So in this example, square root of 45, when we refer back to that list of perfect square factors up top, we can recognize that 9 times 5 makes 45, and 9 is a perfect square factor, so this is going to lead us somewhere. Bottom line, the 9 comes outside of a square root as a 3, and then the 5 stays inside a square root symbol. And so at the end of the day, the square root of 45 simplifies to 3 square roots of 5. And we can actually check that on a calculator in class, or if you have one handy, put in the square root of 45 and see if your calculator tells you 3 square roots of 5. Let's just do another example. Square root of 72. When I look back at the perfect square factors up top, I want to find the biggest one that goes into 72. And so with a little inspection, 36 times 2 makes 72. So we're going to rewrite 72 as 36 times 2, still inside the square root. And then we recognize that the square root of 36 becomes 6 outside of the square root, and the 2 stays inside the square root. So the simplified form there is 6 square roots of 2. Here's an example that involves a variable. So 48, I recognize, is 16 times 3. Again, 16 is the largest perfect square factor that evenly divides 48. Now I want to talk about m to the 5th. M to the 5th is m times m times m times m times m. And we're really looking for groups of 2. So this is an m squared, and this is an m squared, and collectively this is an m to the 4th, right? So we really want to find groups of 2, and there's 2 groups of 2, which means we can make this m to the 4th, and then there's a leftover m right here. Okay, so I know that got kind of messy quickly, so I'm going to erase all that and then just give us our strategy. So the strategy looks like this. First, we attack the number 48, perfect square factor 16, and then I'm doing another group of 3, just like I did up here. Here's my perfect square factor, here's the not perfect square, here's perfect square factor, here's the not perfect square. So following that along. Now, because we have m to the 5th, I'm really looking for groups of 2. All right. And if I have 5 factors of m that I just laid out, I have really m to the fourth and then a leftover m. And where this is all leading, okay, the 16 has a square root of 4, and m to the fourth has a square root of m squared, since m squared times m squared makes m to the fourth. And then these two factors right here stay inside the square root. So with a variable, we want to find inside of square roots groups of 2. There was 2 groups of 2, so really we have m to the fourth with the leftover m. And then closing, the square root of 48 m to the fifth simplifies to 4 m squared times the square root of 3m. A lot of words. So now the goal of the rest of this lesson is really 2 things. We're going to talk about other roots besides square roots, which are called nth roots, predominantly cube roots, but we'll look at some fourth and fifth roots as well. We're going to look at simplifying them. We're going to look at something called rationalizing a denominator. We're also going to talk about adding and subtracting roots. And then lastly, how any root can be expressed as fractional exponents. So that's the goal of this lesson. So there was a little warm up with square roots, but we're now going to extend it into other roots. So the symbol, the nth root of a, which we see right here that I just read, the symbol is called a radical sign. The n is called the index, and the part inside the square root is called the radicand. When the index is 3, we call it a cube root. And what we're basically asking, very similar to a square root says what times itself makes the inside. Well, a cube root asks what times itself makes the inside. So basically, we're looking for a number that when it's multiplied by itself 3 times in a row makes the inside value. And a fourth root, very similar, is a number times itself, times itself, times itself that makes the inside value. Let's look at a specific example. A cube root of 8 basically is asking what number times itself makes negative 8. And the answer is negative 2. The fourth root of 81, we're basically trying to ask ourselves what number times itself makes 81. So something times something times something times something, all times itself, question mark times question mark, has to make 81. What is that something? The answer is 3. So you might be wondering, wait a minute, a few minutes ago, you mentioned negative signs inside of square roots. And I did. I said negative signs inside of square roots are not real numbers. However, did you just notice the negative sign in cube root is perfectly fine? Okay. So when you have an even index versus an odd index, we have to be careful if there's a negative sign inside. Bottom line, things like square roots, fourth roots, sixth roots, etc., any even roots, the inside, fancy word radicand, must be 0 or a positive. In other words, not negative. However, if you have an odd index, like a cube root that we just saw a moment ago, cube root of negative 8, there's no issue, right? So here's another cube root of negative 1,000. What number times itself is negative 1,000? And the answer is negative 10. Oops. Okay. So the answer there would be negative 10. Negative 10 times negative 10 is positive 100. Multiply that by another negative 10 makes negative 1,000. So with odd indexes, there's literally no restriction. Similar to simplifying square roots, we're going to simplify cube roots, fourth roots, or any root. So again, our goal, similar to square roots, is to pull out any perfect nth factors. What does that mean? Let's look at an example. Simplify the cube root of 108. So here's where you would typically do a little scratch work and say, perfect squares are common numbers in mathematics, but perfect cubes a little less rare, but it doesn't mean we can't make a little side list. 2 times 2 times 2, use your calculator. 3 times 3 times 3, 4 times 4 times 4, and so on and so on. So usually the first few, unless you have a really obnoxious question, will do the trick, and there should not be any obnoxious questions, right? So you kind of list the first few of these. If we need more, we can generate more. And we're going to say, all right, which of these numbers, 8, 27, 64, 125, which of these, the biggest one of these, goes into 108 evenly? And the answer, again, just with some calculator work, I found was 27. Right, so this number right here, and it ended up being 27 times 4. So just to make it a connection what we did before, when we had a square root, we wrote the perfect square first and what was left over second, as I call it leftover. So now with a cube root, we're going to write the perfect cube and then what was left over. And then we simply just simplify. The cube root of 27 becomes 3, and the cube root of 4 stays the cube root of 4. This is your final answer. That's how the cube root of 108 would simplify. Simplify the cube root of negative 32, n to the 7th, t to the 5th. So, similar to before, if we focus just on the number part, I'm going over here in my list of numbers, and I notice 8 is the biggest perfect cube that goes into 32. Typically, if you have a negative, we're going to take the negative sign out of the root. So at the end of the day, I'm going to put negative 8 in my first leading group. Similar to the square root example that I did a few moments ago, this is a cube root. We're looking for groups of 3. So 7 has 2 groups of 3, so that means we're going to write an n to the 6. 2 groups of 3 is 6. 5, the exponent of 5, has 1 group of 3 with 2 left over. So I'm going to put a t to the 3rd, and then going back to what I just said, n to the 7th has 2 groups of 3 called a 6, and then 1 left over. T to the 5th has 1 group of 3 with 2 left over. So now when I kind of structure my cube root so that it's ready to be simplified, I put everything that's perfect in this kind of front group right here, and everything that's going to be stuck behind in the second group. So now the cube root of 8 becomes negative 2, the cube root of n to the 6 becomes n squared, and the cube root of t cubed is just t. So all of that first group simplifies. This is what gets pulled out of the cube root, simplifies to what we see here, and that part stays trapped inside. And that's your final simplest form answer. Okay. Simplify negative, which is outside of a fourth root, so no issues here. Negative fourth root of 405x cubed y to the 9th. Again, not that I know these as any better than you. It's just a little bit of side work, like with some calculator. 2 to the 4th, 2 times 2 is 4 times 2 is 8, 16, 30, 16. My bad on that. 3 to the 4th, 81. 4 to the 4th, let's see, that's kind of getting a little bit challenging. 16 times 16, since this is 4 squared and that's 4 squared, but 16 times 16 is, let's do it out. 30. Oh, much easier with the calculator, which I don't have with me nearby right now. 36, carry a 3, 60, 90, 0, 60, and 100. So it looks like 256. And 5 to the 4th, some strange reason, I just know 625. It's a weird fact that I carry with me. But if I didn't, I would multiply 25 times 25. So anyways, when I look at these numbers and with the use of calculator, I did the work ahead of time. I noticed that 405 was evenly divisible by 81. So structuring my perfect factor, my fourth perfect factor. What am I trying to say here? My fourth, like, so we say perfect squares, perfect cubes. I guess this is perfect fourths. That's what I was trying to say there. So 81 is a perfect fourth. Similarly, I'm looking for groups of 4. Well, x cubed is not going to have any groups of 4. So I'm going to structure that in that back group. If I have y to the ninth, I have 2 groups of 4. So I have an 8 that's going to come out nicely, and then 1 left over here. So similar to everything thus far, this is this is the perfect group. This is the group that's going to simplify out, and this is what's going to be left behind. The negative sign stays in front. The fourth root of 81 becomes 3. The fourth root of y to the 8th becomes y squared, because there's 2 groups of 4. And then everything else stays inside the fourth root there. And that's your answer. Onto the quotient property of radicals. Here's an example. The square root of 16 divided by 25. Notice, okay, that if I just to kind of show you what I wrote here, what times itself makes 16 over 25? And the answer is 4/5, right? So notice that's the answer. Also, notice there's an intermediate step. We are legally allowed to take a quotient and make it into 2 square roots. So the square root of a quotient is equal to a quotient of the square roots. Very wordy, but basically you can take a fraction that's inside of a square root and take the square root of the top part over the square root of the bottom part, and it works out every single time. And in general, that's not just true for square roots, for cube roots, fourth roots, and for any root. If you have a fraction inside of a root, you can take the root of the top and divide it by the root of the bottom. That's what this rule says. Something called rationalizing the denominator. So really brief side story here. Historically, this had a lot more meaning before calculators. If you wanted to know more about it, you could look it up yourself. So like the history of like square roots and the denominator. But if I were to give you a quick story, if we had 1 loaf of bread between 2 of us, we could figure out that, hey, we're each going to get 0.5 or half of the bread, right? But in a very strange case, if we had 1 loaf of bread and we had to divide it by square root of 3, I don't know why, but mathematicians and our ancestors that were both scientists and mathematicians wanted to divide by root 3. Without a calculator, it was very strange. So what they wanted to do was change it so that they could divide by a whole number. So that's like the brief history here. Kind of get a little detour there, but one might argue it's not super important anymore, but there are patterns and kind of neat curiosities that fall out from this process still if you took a class in trigonometry, pre-calculus, and even calculus. Furthermore, it's part of the curriculum that we have to go over. So back to the main point, rationalizing the denominator basically is a procedure that makes the denominator, the bottom part, a whole number. And for examples like 1 divided by the square root of 3, it's quite simple. You just multiply by the square root of 3 to the top and the bottom of the fraction. And notice what happens. In the numerator, 1 times square root of 3 becomes square root of 3. And in the denominator, which I didn't show, but I'll just show this one time, we get square root of 3 times square root of 3, which becomes the square root of 9, which leads us back to 3. So a square root times itself cancels out. And so we're left with a 3. And there it is. There's the whole process. It's not that painful. You just multiply by another copy of the square root. And if it was a cube root, well, if you caught what I said there a moment ago, we needed another copy. We needed a total of 2 copies in the denominator for square root to cancel out. If you're following along here, to cancel out a cube root in the denominator, we're going to need a total of 3 copies. So here's the original fraction, and then I'm going to multiply top and bottom by not 1 copy, but 2 more copies. So now when you look at the denominator, what we really have is the cube root of x cubed, but notice that simplifies to x. And in the numerator, we have 1 times the cube root of x times the cube root of x. So you have an exponent of 2 on the inside of the radical sign there, right? That's what it means to rationalize a denominator. We're only going to look at square roots and cube roots in this course. Here's an example that uses both the quotient property and rationalizing. So if we were to ask to simplify the square root of 45 over 32, we could recognize, okay, I want to think back to my perfect squares that are going to get pulled out. 45, I know is 9 times 5. And then in 32, I recognize it's 16 times 2. So I did 2 steps here, kind of in one. I applied the property that says the square root of a fraction is the square root of the top divided by the square root of the bottom. I also started to set it up about what are my perfect square factors that I just talked out loud. Now, the 9 becomes a 3, the 5 stays inside, the 16 becomes a 4, and the factor of 2 stays inside. Okay, so that's where I'm at this point. Next, I noticed that there's a square root in the denominator here, just like we had up there. So I multiply by another copy of it to rationalize the denominator. And so at the end of the day, we have 3 times the square root of 5 times the square root of 2. That becomes 3 square roots of 10 in the numerator. And in the denominator, we have 4. Remember, just talked about this a few minutes ago. This becomes a 2. So 4 times 2 makes 8. And that's your final answer. In the next examples, we're going to deal specifically when there's 2 terms. And we're only going to deal when there's square roots. Okay. So in the previous examples, there was only 1 term. There was like the square root of 3 or the cube root of x. Now, here's an example that says 7 divided by 5 plus the square root of 2. There are 2 terms here. And they're not like terms. They're not going to combine. So here's a must know. You're going to multiply the top and bottom by the first term and the opposite of the second term. So our first term is 5. So we're going to keep the 5. And then the opposite of adding 2 is subtracting. The opposite of adding square root of 2 is subtracting square root of 2. So that's what we multiply the top and bottom by. The opposite of the sign in between the terms. Okay. When we look at the numerator, we distribute the 7. It becomes 35. When we distribute the 7, we just throw it in front of that square root symbol. In the denominator, if you FOIL this out, okay, so if you did 5 times 5, and then 5 times negative root 2, and then positive 5 times positive root 2, and then a positive times a negative, and we already discussed a few times that that's going to become 2. Notice that the middles cancel out, and this will happen every time. So the shortcut here, and this will work every time, is to recognize when you multiply by 2 terms that have different signs in between them, they're called conjugate pairs. It's a fancy word in mathematics, but you're going to square the first number, you're going to square the second number, which just becomes 2, and the sign in between them is always minus. 25 minus 2. Actually, for those who are making a connection, when we talked about factoring polynomials, we said a squared minus b squared is equal to a difference of squares. That's exactly what we're doing. We have two terms multiplied by two terms whose signs are different in between them. That's always going to equal the first term squared minus the second term squared. So that's truly what's going on there. All right. Rationalizing the denominator with two terms, you multiply by a conjugate, which is just a fancy word for change the sign in between. You distribute on the top and in the bottom. You square the first term minus square the second term, and we're done. Let's see if we can do that as elegantly as I just said it. I have two terms in the denominator with a minus, so I'm going to write it with a plus. We're going to multiply top and bottom by square root of x plus square root of 10. We're going to distribute on the top, which simply means throw with the 2 in front of the square root of both those symbols. Bada bing, bada boom. And in the bottom, you square the first term. So a square root of x squared becomes x. You square the second term, square root of 10 squared just becomes a 10. And there's a minus sign in between them. And in this example, that's it. We're done. There's nothing else to simplify. Adding and subtracting radical expressions. So here, very simply, you're just going to take what we did earlier about simplifying either square roots or cube roots or whatever root you have, and then you just combine your roots. So we'll just kind of look at this example. So square root of 12 times 5 plus square root of 75. So I want to simplify the square root of 12. Again, going back to recognizing my perfect square factor is 4. That's going to be left over. And in the square root of 75, 25 is my perfect square factor. 3 is going to be left over. The square root of 4 becomes 2. And then it's going to hit up this 5 in front to become 10. So 5 times 2 becomes 10. And the square root of 3 stays inside. Square root of 25 is 5. Square root of 3 stays inside. Right, so there's our simplifying of each one of those square roots. Now recognize that these are like terms. We actually call them like radicals. 10 square roots of 3 plus 5 square roots of 3. It's very similar to like saying 10x plus 5x. 10 secret numbers plus 5 secret numbers is 15 secret numbers. Very similarly, 10 square roots of 3 plus 5 square roots of 3 is 15 square roots of 3. You just combine the number of parts. An example with a cube root. We want to pull out any perfect cube roots inside of 54. So 27 times 2 makes 54. And in 128, 64 times 2 makes 128. Just reminding us we talked about the cube roots up here. These numbers, here they are again. So if I needed to pull them out, I could. But anyways, keeping this nice and clean. So here's my perfect cube. That's going to stay put. Here's my perfect cube. That's going to stay put. Okay, the cube root of 27 becomes 3. And then it's going to get multiplied by that outside 7. So we're going to have a 21 outside. 2 stays inside. Cube root of 64 is 4. It's going to get multiplied by that 6 to be 24. 2 stays inside. And at this point, 21 cube roots of 2 minus 24 cube roots of 3 cube roots of 2 is negative 3 cube roots of 2. It's the last part of the lesson. Rational exponents. Any root, square root, cube root, fourth root, any root can always be written as a fractional exponent. So this is a must know, okay? Where the index, vocab word from earlier, becomes the denominator. The radicand, the inside part, becomes the base, and that exponent right there becomes the numerator of the fraction. So as an example, the square root of 9, we all know is 3, right? But if someone were to ask me, write the square root of 9 using a fractional exponent, notice there's an invisible 2 for my index, and there's also an invisible 1 on the inside 9. At the end of the day, the square root of 9 can be rewritten as 9 to the 1/2 power. And if you have a calculator nearby, please check that. It will give you 3. Another example, the fifth root of x cubed. My index is 5. It becomes my numerator. The inside exponent is 3. That becomes my numerator. Did I just say that wrong? My index becomes my denominator. The 3 becomes the numerator. Anyways, it was written correctly. And x becomes the base. So your final answer is x to the 3/5. The fifth root of x cubed is the same as x to the 3/5. Since we can take radicals and write them using exponents, our exponent rules from a few lessons ago are back in play. For instance, the example shown here says take the cube root of y to the 5th divided by the square root of y cubed and rewrite that as y raised to a power. So the numerator has an index of 3 and an inside exponent of 5. So the fractional exponent is going to be 5/3, which is written right there. In the denominator, the invisible index is 2 and the inside exponent is 3. So the denominator can be rewritten as y to the 3/2, as we see right here. Now, property of exponents state that if we have the same base being divided by each other, then we simply subtract the exponents. So 5/3 minus 3/2 becomes y to the 1/6 power. And that's your final answer. And arguably, that is definitely simpler, okay, than what we originally saw. And if you were to take a calculus course at some point in your future, you would want to get to the simplest form. So there's still connections that this is applied in calculus. You might say, I might never take calculus, but you don't know what's in your future. So you'll have this in your background if you do. Last but not least, kind of just a silly example here, but we have the square root of the cube root of y squared. So notice I have an outside square root, reminding us earlier the index is 2. So there's my 2. And I can say everything inside here has an exponent of 1. So that's the structure there. Now when I focus on the inside parentheses, I have an index of 3 and an inside exponent of 2. So this piece right here becomes y to the 2/3. If you need to, go back and look at that again. I'm going to just highlight it this time. Here's my inside. That becomes y to the 2/3. And then my outside has an index of 2. So that's how that's structured. And then going back to property of exponents, we remember that stacked exponents multiply. And so 2/3 times 1/2 becomes 2/6, which simplifies to 1/3. So that's our lesson on radicals. At the end of this lesson, you now should be able to simplify square roots, simplify cube roots, fourth roots, fifth roots. You should know that if you have an even index, we can't allow a negative on the inside. The answer would be not a real number, but if it's an odd index, there's no problem. You should be able to use the quotient property and rationalizing both square roots and cube roots in the denominator. You should be able to rationalize expressions that have 2 terms involving a square root in the denominator. You should also be able to add and subtract radical expressions, and finally rewrite radical expressions using fractional exponents. There is an assignment for practice in my lab that'll be due as usual a week from Monday. I look forward to seeing everyone back in class this coming Wednesday. I hope you had a great Thanksgiving and see you Wednesday. Take care.